So we have learned how to take time derivatives of quantities that are functions of other quantities which only depend on time. So in this problem that we did, u was a function of time only, v was a function of time only, and omega is a function of u and v, that in the sense that omega is equal to u cross v, and we wanted the time derivative of omega. That's pretty easy to do. We first write this equation in initial notation and then take ddt of that, remembering that Eij, Eijk and Ek, these things are fixed and they are not affected by the ddt outside. That's what we did. Now we get into slightly more complicated territory. Um, we have to generalize the idea of a gradient. So let us try to do that by um, taking the example of a scalar valued function of a second order tensor. So um, okay, a scalar valued function of a second order tensor can be written like phi of, let's say, a second order tensor A. Now, when we think about the gradient of this, what we are basically asking is that if I change a by a small amount, then how much would phi change? So we are basically asking that if I change a to a plus dA, then what would be d phi? So this is what we are asking. So we had done this in your calculus, basic calculus courses. We said that phi d phi dx, where phi is a function of x only, is phi x plus, or let me do it in a different way. So when we did functions of one variable, let's say scalar function of a scalar variable, then we wrote phi x plus, let's say, dx as phi x plus d phi dx times dx plus d phi d square phi dx square 1 by 2 dx square, and so on. This is called a Taylor series. Okay. Now, this is what we did for one variable. So now what we are going to do is, we now have phi of a second order tensor, a scalar valued function of a second order tensor, and we want to write phi of a plus dA. Okay, so I have changed a by a small amount. I have changed a by a small amount, and I need to know how much phi changes. So I'll write this in the Taylor series. So phi of a plus, I had in the scalar function of a scalar variable, that is for phi x, I had in the first term d phi dx, right? So here I will have, let's say, del phi del a and dA as the first term, and then I will have terms of uh, the order dA square, which we will not talk about right at this moment because we are interested in the first derivative here. We are interested in the first derivative. Remember, the first derivative comes in the term that is linear in dA, just like here the first derivative came in the term that was linear in dx. Now look at this function. So a is a tensor. A is a second order tensor. So dA is also a second order tensor. The change in A is also a second order tensor. And phi is a scalar. So this quantity must give you a scalar. So a second order tensor and another quantity can give you a scalar only when you put two dots here. Okay, that means if you put two dots here, this quantity will be a scalar provided this is also a second order tensor. So what we now see is that the first derivative of phi with respect to a is itself a second order tensor, which is written like del phi del a, and whose components would be, because a is the only tensor here, second order tensor here, phi is a scalar, its components would be del phi del ij, ei, ej. Remember, we sometimes drop the dyadic and write two vectors side by side. That means a dyadic product. So this is a second order tensor. We have shown that this has to be a second order tensor, and this has to be a contraction operation. Otherwise, this whole thing cannot give a scalar. And that's what we need on the left hand side. We need this to be scalar. So this is how you take the gradient of a scalar valued function of a second order tensor. Okay, so this is the gradient of a scalar valued function phi with respect to a tensor A. Okay, so this is how we take derivative of phi with respect to A, and the result of that is a second order tensor with components del phi del aij in the I x1 x2 x3 coordinate system, fixed Cartesian coordinate system. Now as I said, the options are unlimited. So here I have just looked at a scalar valued function of a second order tensor. I can have a tensor function of a tensor, a vector function of a tensor, and so on and so forth. Many combinations are possible. And in each case, we will have to carefully look at two things when we talk about the first derivative. When we talk about the first derivative, the two things that we have to look at is what is there on the left. When we write this Taylor series expansion, what is there on the left? Here on the left you have a scalar quantity. So this term, the first term in the Taylor series expansion, should give you a scalar quantity, and that would mean that you have to look at the order of this. If this is a third order tensor, if this is a third order tensor and you need a scalar, then you need to have this operation correctly defined in a way that this gives you a scalar quantity. So you have to look at the nature of this quantity, which has to be a third order tensor, and nature of this contraction operation, which for two third order tensors has to be three dots, here. So every time we look at the gradient of a physical quantity with respect to another physical quantity, we have to carefully see what kind of an animal the derivative is going to be. Like in this case, it's going to be a second order tensor. So what kind of an animal is going to be, and what kind of an operation do we need to have for the second term in the Taylor series? Let's take this a little further. Okay, let's take this a little further and look at a few uh, interesting cases. So this is what we just did. Now let us look at this quantity. Okay, so we have a scalar, we have a tensor valued function, second order tensor valued function of another tensor. So let's say we have a tensor valued function A whose variation with respect to another tensor B is. So we have a function A which is itself a function of another tensor B, and we need to this. Now if you do this Taylor series expansion thing that we did, now you would realize that you need in the first term, where you write the derivative, you would write del A, del B, and dB. This is what you will write for the the second term on the right of the Taylor series, right? Now this whole thing has to be the same dimension as A, which is a second order tensor. So this has to be a second order tensor. This itself is, the argument is itself a second order tensor. So this is a second order tensor, and this has to be such an animal that will give you a second order tensor as a result of this entire operation. So immediately we see that this has to be a fourth order tensor, and this has to be a double contraction operation, which will give fourth order tensor multiplying a second order tensor will give you a second order tensor, which is what you want on the left hand side of the Taylor series. Therefore, del A, del B, where both A and B are tensors, will be del Aij, del BKL, EI, EJ, EK, EL. So this would be your second order tensor del A, del B. So these would be the components in the Cartesian system, Aij, del BKL, and this is how you will write the second order tensor. Okay. Now let us use this to work out a problem. So I need to find a tensor which is where the inverse of the tensor is uh, the derivative of the inverse is taken with respect to the tensor itself. Okay, so what I'm going to do is going to take del A inverse of del A. Now A is a second order tensor, so A inverse is a second order tensor. So this quantity would actually be a fourth order tensor, which we denote by this. So this would be a fourth order tensor, as we have learned. A inverse is of course a function of A. So so I will derive this from first principles. So what I'm going to do is I'm going to use this idea that A times A multiplied by A inverse is equal to I. I'm going to start from there and work with indicial notation. So let's see how we can. So I'm going to do A inverse A is equal to I. So obviously, if I take the derivative of this, the right hand side will be equal to 0 because I is a fixed tensor and doesn't depend on space. So if I take derivative, doesn't depend on A. So if I take the derivative of this with respect to A, I should get 0. So the ijklth component of the derivative of this whole thing with respect to A should give me equal to 0. Now I will use the indicial notation to write it, and I will use what I learned in the previous slide. This is what we have learned, and I'm going to use this to derive what are the components of this. Let's see how we can go about doing this. So okay, let me clear this. So now we have del A of A inverse A. This is what we have, and we know that the ijlth component of this, any ijlth component, is equal to 0. This is what we know. Now I'm going to write A inverse A from what we have learned. So the ijth component of this and divided by the klth component of this. So this is my this has to be equal to 0. This is equal to 0, right? Now ijth component of A, so A inverse A, the ijth component of that can be written as A inverse I k A k j, right? So I write that. So A inverse right, from here I come to here. Okay, so if you are with me till now, let me try and erase some bit of it. Now let us work with this. So let's go from here. So then I will write I will do it in just like a regular derivative. So I'll have a kl a I k inverse and then a kl. Oh no, this is j. This is j plus a I k inverse del del a. I did I have used k too many times, so this is something that you should avoid. Okay, so here I should not have used this k because k was already there here. Okay, so I should use something else. Let me use, let's say, n I n then n j. So I used k more than twice, so that confuses the relation, so I shouldn't have done that, and you shouldn't do it either. Now I can take the derivative. So I take del a k l a I n inverse and a n j remains, plus now a I n inverse remains intact, plus del a k l. This is just chain rule, n j, that is equal to 0. Okay. Uh, Now remember that this is the thing that we want to get. This is the thing that we need. We need the derivative of a function with respect to derivative of a, derivative of a inverse with respect to a. That's what we need. So now drop this off. Okay. So this is the thing that we need. We have to extract it. So now we have del a k l a I n inverse a n j is equal to minus a I n inverse del a n j del a k l. Now look at this quantity. This is del a n j with respect to del a k l. So whenever n is equal to k or j is equal to l and j is equal to l, whenever n is equal to k and j is equal to l, you get 1 here, otherwise you get 0. So this will become now minus a I n inverse delta n k delta j l. So this whole thing will be equal to 1 only when n is equal to k as well as j is equal to l. That's only when this quantity will give you 1. Otherwise, this quantity will give you 0. So this does the same thing. It gives you 1 when n is equal to k, j is equal to l, and gives you 0 otherwise. Now this n will be knocked off in favor of k. So you will get minus a I k inverse delta jl as the right hand side. Now on the left hand side, this is what we need to find out, and this is what we should get rid of. To get rid of, we can multiply this with A inverse. So what we can do, we can multiply with, let's say, j m inverse on both sides. So we can multiply with Jm inverse on both sides. When you multiply with Jm inverse here, this becomes delta Nm, right? So when it becomes delta Nm, this N knocks off this N in favor of the N. So you will be left with del A inverse Im by del A KL, and on this side you will be this J M and J L, this J and this J will knock each other out, so you will be left with minus A I K inverse A, J will be knocked out in favor of L, A L M. So this is what we get. So this is what we wanted, and that's equal to this. That's what we have shown. Now, okay, so here we were, so we got this, and the way we got this is by taking this to be equal to 1 when n is equal to k and j is equal to l. So nk jl, delta nk delta jl is the result of this derivative. However, there's a small bit of subtlety here, because we have also been told that in the problem that this is a symmetric tensor. Therefore, not only would this be 1 if n is equal to k and j is equal to l, it will also be 1 if n equal to l and j equal to k, because nj and jn and kl and lk are the same for this tensor. So therefore, this will be 0, this will be equal to 1 for this when this happens, also when delta NL delta JK. So both of these would give you, so half of this would give you the correct derivative of this when A is equal to a symmetric second order tensor. So why this half? Because both of these would give you the same answer, and the actual answer is half of that. So we are taking care of both the possibilities here, and halving it, because, so that the end result is the same as for a non-symmetric tensor. But we have to do this because for a symmetric tensor, this would be 1 even when n is equal to L and j is equal to k. It will be 1 for when n is equal to k and j is equal to L. That's taken care of by this term. And then n is equal to L, j is equal to k is taken care of by this term. So that's what is done in the notes. So let's go back there. Yeah. So this is what is done. This derivative, because we are told that the A is a symmetric tensor, this derivative is taken in this way, and this is the answer to your Bijinkl, which is what we set out to find. Obviously, we wanted to find Ijkl. Obviously, you can replace n by j on both sides and get Ijkl as well. This is a rather long way of doing it. Um, we generally don't do it like this, though this particular relation is an important relation. What we rely on most of the time is the nabla operator. So this nabla operator is an operator. It's not really a vector, but what we do is we treat this thing as a vector. And that simplifies the operations quite a lot, at least in the Cartesian coordinate system. In the Cartesian coordinate system, treating this operator as a vector makes life much easier. So let us see how this helps us. Let us now remember this nabla operator. So this nabla operator is sorry, let's clear this. So we are defining this vector, which we are denoting by nabla, as with components del xm. These components are not really numbers, they are operators, times em. Let's say this is how we are denoting it. Now what we want is let's say gradient of a scalar field. We want to find the gradient of a scalar field. So we know the gradient of a scalar field is going to be a vector, a first order tensor. So let's say we have a field phi which is a function of the position, say temperature as a function of position, and we want gradient of this. So we the gradient or the nabla operator here. This is also called the gradient operator. So this is the gradient operator or the nabla operator. I'll call it both. So when you do this, this is how you treat this as if it's a proper multiplication between a vector and a scalar. So you do it like this: del x, and the first vector is this, and then you have a scalar phi. Now this del xm will not act on this em because these are fixed vectors, but it will act on this phi because this itself is a function of x. So what we will have is del phi del xm em as gradient of phi. So gradient of phi, where phi is a function of position, will be given by a vector whose components, whose mth component is del phi del xm. So that's how we do it for a scalar function of the position vector. Now let us go back. We want to do divergence of a vector. Okay, so divergence of a vector field. So again, we start with the nabla operator, divergent gradient operators, which is del xm em, and we need to do the divergence operation on a vector v, which is itself a function of position. So I can write the first one as del x k ek, the first vector, dotted with the second one is also a vector. So I write vm em, where remember v is a function of x. So again, this doesn't get affected by this operator, and Vm gets affected by the operator. So we have del Vm del xk, ek dot em is delta km, and the k knocks off in favor of m. So del Vm del xm is what we get. Both v and m are repeated indices, so this is actually a sum, del v1 del x1 plus del v2 del x2 del v3 del x3. And also one thing to remember is these kinds of derivatives, we will very often denote them by v, m, comma, m. So vi, comma, j would mean del vi del xj. So this is what it will mean. So this we will be writing as vm comma m. Okay, right. So let's go back again. Curl of a vector field. That's also possible to do using what we have learned. So we have again the nabla guy, right? And we have a vector field v of the position vector x, which is vm, which is functions of x1, x2, x3, em. This is how we write it. And then we want to take curl of v, and that we know. Now we treat this as a vector and this as a vector operation. We know that this is e I j k del x j, right, v k. This is what we will get, and this sorry, this would be the ith component of this I'm writing. If you get confused by this, I will write it in other ways. I'll write it in, so let's see, there's this. Maybe you will get confused by this. Okay, so we need to do this, and what we do is we write del x m, the first vector em, crossed with v k e k, let's say, and then again this does not operate on this. This is a fixed vector, and we know the cross product is written as e, let's say, I j k del x j v k and e I. So we know that we know what em cross ek is. It's e I j k e I I m k I m k e I. So that's what we have used here, and this operator does not work on any of these. So uh, ijk del vk del xj ei. So the ith component of v cross j, so the ith component of the curl of v is equal to eijk v k comma j. So this would be the ith component of the curl. Okay, we can carry on like this, and we do need to carry on like this for some more complicated uh, so now let us look at the gradient of a vector field. So this is something that you have not done before. So you would have done the divergence of a vector field, um, but you, and the gradient of a scalar field, but you have not done the gradient of a vector field. But that's not unthinkable, because now we have this guy, right? And we want to take the gradient of a vector field. So gradient of a vector field will be, gradient of a scalar is a vector, so gradient of a vector would be a second order tensor. So what we will do is we'll do this. So the gradient operator dyadic with v uh, will give you, we know what the properties of this are. So if you have a dyadic b, it's aibj ei ej, that's what you get. So if you do this, then you will get del x I, those are the components of the nabla operator, and then vj ei dyadic ej, so vi comma j ei ej. So this is a second order tensor. So the gradient of a vector field, so this is gradient of a vector field of which depends on position. So gradient of a vector field is a second order tensor with components equal to Vij. That's what we have shown here. So again, uh, divergence of a tensor field, second order tensor, it's done in again the same way. Let's clear this. So let's do, so okay, so we want to do this of a tensor field which is a function of position, and it's exactly done the same way. So del x m em, that's the first vector, that's a nabla, dotted with t pq, let's say ep pq, that's how you write a second order tensor, dot this, and you will get uh, del del xn delta in q t eq ep, okay, and t pq delta t pq del xn ep is the answer to this. That's the answer to this. Okay. We can carry on like this. We can get, we have got divergence, we can get a gradient of a tensor field in the same way. So it's a third gradient of a second order tensor would be a third order tensor whose components are Tij comma k, Tij comma k. So for all fields which depend on position dependent fields, we can get we can use the nabla operator to get divergence, curl, gradient, and so on and so forth. Treating curl, treating the nabla operator, treating the nabla operator as a bona fide vector, That's the trick that we use. Now there are two important operators that will come in handy. One will come in very handy, which is the Laplacian or harmonic operator, which is the divergence applied twice. So divergence dot divergence applied twice on some function of position. Other is the Hessian operator, which is uh, uh, the gradient operator or the nabla operator, dyadic of that operator on some function. Let's see how they look like. So the first one is nabla dot nabla on some function, and that is sometimes denoted by nabla square, also called the harmonic operator or the Laplacian operator. So this is some function of a position. So this first one is a vector del xi ei. The second one is a vector del xj ej, and then you have this something which can be a scalar vector tensor, whatever the case may be. And then you have ei dot ej is delta ij, which gives you del square del xi square of that something which can be a vector scalar tensor. So ultimately you get a scalar quantity. This is a scalar quantity because you have a dot product of two sort of vectors, not really vectors, operators they are. So the operator is a scalar, is something that gives you a scalar. The Hessian, as you can imagine, these are two vectors and you have the direct product of them. So what you are getting is a tensor, is a second order tensor. So that's the difference between the two. So for the Hessian, what you will get is the second order tensor, second derivative with respect to xi, xj, ei, ej. So this is a second order tensor that you will get from the Hessian. Hessian is something that we don't use too much in this course, but it's very important for elasticity theory. Higher elasticity theories make use of the Hessian quite a bit. We won't, but we would use this. So I want you to understand the difference between the harmonic operator, which is actually a dot product between the nabla operator, and the Hessian, which is actually a dyadic between the nabla operator. Okay, let's stop here.